I noticed that I have recently been more willing to read things more critically and have an open mind for challenging them, not necessarily because I am trying to find mistakes in them, but just to understand them at a deeper level. And recently there was a success story for me personally when I was looking at the definition of BMO functions, and I just noticed that maybe we could change it a little bit to a more intuitive definition, and that's what I am about to explain to you. The setting is a metric space, and there's a Borel measure on X, so in particular the open balls are measurable, and we assume that the balls have positive and finite measure. If you have seen or if you look up any recent modern paper on BMO spaces, a definition you might face is as follows. You call it BMO if this norm is finite. So that is kind of a standard nowadays, all too common definition they give for BMO. And if you find this elegant, I'm not sure how you're thinking about it, because there's nothing elegant about it, and that's part of changing our attitude here. If something is too technical, doesn't mean it's deeper. Personally, I would say that this definition is not a suitable definition. It's just there's too much clutter in it. Personally, for me, I was under the impression, maybe it's just me, okay, so this is just very personal, that the fact that you subtract the integral average of f itself from this is playing a significant role, and if you ask people why are you subtracting f of b, they would maybe rightly say that, well, what else makes sense? If you want to talk about oscillation of a function, you just compare values to the average. And to me, it seemed like this definition would work only with this value in that. And also, this is why we assume upfront that it's L1 looks, so that this number is well defined. Okay, so first of all, there's a lot going on here just to be able to make sense of the expression. Second of all, if we are truly talking about functions with a certain property, there is no need for us to also, at the same time as we're defining them, we're isolating them from all other functions. So it's not necessary at all to at the same time say that this is actually a norm. That means it scales the right way and there's triangle inequality. And this also assumes or it tries to get the message across that all of these functions together will build a vector space, a normed vector space. But before we do all of that, you should first explain why BMO are interesting, why are they natural, and what is the key property that makes them worth defining. Imagine defining continuity, but at the same time saying that the space of all continuous functions on a compact space form a Banach space, or something like that. That's not the point of continuity. So if you're defining continuity, you don't talk about the Banach space of all continuous functions in the same line. So when I was reading from an appendix to Gromov's book written by Sims, so by Stephen Sims, based on a suggestion from a friend, I started reading that appendix, which is 100 plus pages, and he had beautifully explained the whole notion of BMO, and the key notion there was that BMO function is almost constant on every ball in a measure theoretic sense, and there's some uniformity assumption. And based on this point of view for BMO, I was saying, well, maybe we can just start the definition by that. How about this? So a measurable f, not L1 look, I'm not assuming that, belongs to BMO if there exists some C, that will be the uniformity part, with the property that for every ball there exists some constant value such that on average on the ball the function is close to that constant. So this constant changes from one ball to another, but what percent of the ball, on what percent of the ball f is close to that is uniform. So that's why we start with there exists C and so on. Okay. Of course, definition 1 implies 2, because we can take these ABs just to be FBs, but the question was, does 2 imply 1? Right? So if these two definitions produce the same class of functions, I'm not talking about the norm or vector space properties. If these two classes of functions produce the same thing, I would rather go with the second one, because to me it just goes to the core idea behind BMO, and it just says that on a good portion of every ball f is close to some constant, and at this point we don't care if that constant is the average of f over the ball or some other constant. I wrote a question on MathStack Exchange asking whether the two definitions are equal. I asked a couple friends who also immediately gave me a proof. The proof is simply just triangle inequality, as Martin here, thank you Martin, mentions. And it's always true that if you have definition 2 with C, then you get definition 1 with 2 times C, because that 2 appears due to the triangle inequality. To my surprise, I learned that actually the original definition used a constant and not the average of the function over the ball. Indeed, here they use cubes, parallel cubes to the coordinates in Euclidean spaces. That is the same basically to using balls, but in metric spaces, of course, you don't have canonically defined cubes. So I think the moral of the story is that even in very famous definitions, if you find something kind of too tricky, if you see something too technical and the message, the idea is hidden, just give it a different try and see what is actually behind the thing. Either you find a simpler definition, like in my case, I personally would prefer the second one, or you just understand why, or the reasoning the original definition had to be the way it is.